Hi, today we're going to be doing a singly linked list with a tail. It's going to be a list implementation. We're going to use list ADT, I believe. So we're going to start with the linear node class. So I've already created a class in IntelliJ. It's called linear node. I think we should extend list ADT and all that stuff. Actually, I think we've already done a video on this, so I'll try to put it in somewhere where you can find it. But I already have a list ADT class here, so you can pause the video and copy this, or just watch the previous video. I think I did it in the array list implementation. So we implement iterator. We have public interface list ADT extends iterable. So list ADT just defines the interface to a general list collection. Specific types of lists will extend this interface to complete the set of necessary operations. Takes parameter type T, because we're working with generics again. So the methods are, so this is a general list ADT. Again, we have an ordered list and an unordered list. We're going to be doing both of them. So the general list ADT interface just has remove first, at least in this implementation. I did do, so this is all my code, aside from the interface. The singly linked list is mine. We're also going to do a doubly linked list with tail, and we're going to try to do one with sentinel nodes as well. I did do some extra methods. I think we might do them in doubly linked lists instead, so don't worry about it. So we're doing public T remove first, remove last, remove first, last, contains, is empty size, iterator, and toString. So it's going to take us probably a couple hours to do it. So we have list ADT, we'll have ordered list ADT, it just has one method. It extends list ADT, it extends the interface. Then we'll have an unordered list ADT, we're going to be using that. It just has three methods, so again it only differentiates in the adding portion of it. So the adding methods are the only thing that makes them different from an unordered to an ordered list. So unordered list, we're going to add to the front, add to the rear, and add after. I think I did an index of as well in the doubly linked list, so we'll do that after. So you can copy those, or you can just see the previous video. I'd recommend seeing the previous video because I discuss what they are and stuff. So we'll close out of those. We're going to start in the linear node class. We've done it before, we're going to do it again. So this one is, because I've changed it, because I've done a singly linear node, and I should have called it a doubly node, but I didn't. For the doubly linked list, but we used a linear node with doubly node, so it had a next and a previous reference, a head and a tail, well, in our list, but it had a next and a previous, and this one we're just going to have a next reference. So we're only going to be able to traverse from the head, because if we use the tail it won't be able to go back, I believe. So we're going to start with that. So I do have some binaural beats in the background today, just because it's going to be kind of boring, so we'll just start. It may be boring for some people, hopefully not. But just not boring, but like to make it a little bit more interesting, trying to make it interesting. So public class, a linear node of type T. And that's it. we're going to have a private linear node of type T next. So next reference no previous for this one. And it's just a private T element. So again, every linear node has two fields. It has a private linear node next and a private T element. Then it's going to have a constructor, public linear node. This one's going to create an empty node. So next is going to point to null. And element is going to point to null. You can say this dot element as well if you want to, but we don't need to. So we'll set element to null. I can just write here, creates an empty node. So you might have seen this if you've watched the other videos. I've started uploading them, but it's just good practice. So here we're going to overload the constructor. Public linear node T element. Next points to null. Next equals null. Then we'll say this, we'll use this keyword now, this dot element points to the element parameter. So this dot element, referencing the instance data, points to the parameter element. Then we'll create some accessors or getter methods. So public, actually we can just link these because they're not that different. They're all related. So public linear node of type T, get next, return next. You can return this dot next as well. Doesn't really matter because this is used in different languages too, like JavaScript and stuff. It's up to you, whatever you want. I think I did do that one time or a couple times, but it's easier just if you don't need this keyword like here, then there's no point in using it, because it could just make it confusing when you're really looking what's accessing the instance data and what's accessing the parameters. I actually thought I already did this video, but I guess not. I might have just coded it without recording. So get next. We'll do a set next to. Public void set next. Takes a parameter linear node of type T node, or whatever you want to call it. Then we'll say next points to node. You could have called it next as well, but that's fine because it's a node again. And the next here, I guess they're both nodes. So you could have said next, but node's fine. Whatever you want. So this part is in my code. It's this is from the Java Foundations textbook. The list implementation itself is my code. I spent a few hours doing it. Maybe last weekend. It took me like 3 hours, I think. Maybe 2. So set next. Then we'll do get element. Public T, because it's a type T. Get element. Then return element. Then public void set element takes T. Whoops. Set element takes a T element. Set element. Okay, so get next set next, we have get element, and then public void set element takes a parameter t element, and then we'll set, we'll use this keyword again, so this dot element points to element. So that should be it. You can create the getters and setters for anything else we missed, if we did. Actually, I don't think we did miss anything because we have next and element only. So we have overloaded constructor. So 2 constructors, get next, set next, get element, set element. So we have everything here. What's it saying here? Okay, I have a lot of classes in here, so it might just be, I might have to delete those actually. So we'll just leave it for now. So it should be right, public class linear node of type T, private linear node of type T next, private T element, public linear node constructor. I'll just write that out just in case anybody doesn't know. It's a constructor. And constructor set the object up with its instance data and parameters, or fields and parameters if you're coming from C. This one says this one is an overloaded constructor. Same thing, just takes a parameter. So when the compiler, the Java compiler, looks for, when we instantiate our object, it's going to say, okay, well, when we create an object, it's going to have one with a parameter, probably. So it's going to be like, okay, well, there's only 2 constructors. So we're going to take the one that just takes a parameter because we need a parameter. And if there was one that took 2 parameters, if we had another constructor that took 2, and we passed in 2, then it would take that one. I think it also differentiates between types as well. I think we did a video on that. So it should be able to identify the constructor. But I think if you have the same types and the same number of parameters, it won't be able to differentiate and it might throw an exception. So just be careful with that. So that's it. Empty collection. We've already done that. If you haven't done that before, you can just copy that. We might have to do a few more. We don't have to worry about it at this exact time. Actually, we probably will. So it's just public class empty collection exception. It's an exception class. It extends runtime exception, which makes it makes empty collection exception a runtime exception through inheritance. It just has the constructor. It takes a string parameter. Then it calls the super reference, passes the string the plus the string you pass in, plus is empty. That's all it does. It just tells you the collection is empty. The data structure is empty. That's it. So now we'll do the general list. I think you can make it abstract. I think. Because we don't actually instantiate a linked list. We instantiate an unordered list and an ordered list, so it's a little confusing. But in the array list, we did make it abstract. Yeah, I think the textbook gave us like just it gave me the first part in the constructor. It didn't give me any methods. I don't believe it was abstract, but you can make it abstract, I think. You can try making it abstract if you want. We can actually try doing that. So we're going to have a public class linked list. Do I have one here? Linear node, deck q, 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 deck q, q built in. don't think we have one. So we'll right click our src folder, click new, and then new class. We'll call it linked list .java. Hit enter. So we'll just rewrite this public class linked list of generic type T. We can implement list ADT, or we can add that at the end, doesn't matter, but it should be fine. So there's going to be lots of errors because it's going to say we didn't implement the methods. Just have a sip of my water, sorry. Actually running out too, have to fill it up. Fill my cup up. Okay, so hopefully you've created that class. And you've extended the list ADT interface. You can pause the video to do the interfaces if you don't already have them. So we'll start with the instance data. So every linked list is going to have its own instance data as well. So it's going to have a protected int count. It'd have a protected linear node of type T, head, and a tail. We'll do it in one line. And then we'll have a protected int mod count. That's for the iterator. We might actually have to go back and do the iterators as well. Try to work with them. So here we'll have the public linked list constructor. There's only going to be one constructor, so we'll set count to point to 0, head to point to null, tail to point to null, and mod count also set to 0. So what are we going to do first? We'll probably not do the remove methods first because that would be confusing. We're going to come back. So we can start with the easier methods, why not? This will probably be like a 3-part video. So we're going to do I'll try to do it quickly. So public T first throws empty collection exception. I do not want it formatted like that. So if is empty, what happened there? If is empty, then we will throw new empty collection exception. We'll pass in linked stack. Whoops. Linked stack. No, whoops, not linked stack. Linked list. I think when I wrote the notes I put linked stack by accident. Okay, so we'll do return head.getElement. So all we're doing is we're referencing the head node, and we're just saying pass us the value, return us the value, or get the value for us. That's it. Last, you can probably guess what we're going to do. So again, for last, if we don't have a tail reference, we would have to traverse with the head. But since we have a tail, we don't need to, and we can just get the value from the tail. Because in some singly linked lists, I think even maybe most of them, you might not have a tail. Usually maybe just in a doubly linked list you'll have a tail. Just depends on who teaches you or what book you learn from. So public T last. If is empty. Not return. Throw new empty collection. Exception. Linked list. And then we'll return tail.get element. That's it. Just returning the tail. The value that's the tail is pointing to. Then here we'll do the is empty. So public boolean is empty. Oh yeah, so I apologize if you didn't know what it was. It's just gonna tell us if it's empty or not using a boolean. So it returns true if count is less than or equal to 0. Actually, it didn't light up, so I thought we already did it. But it lit up. It's not red because we have an interface, and it thinks that we already have it because of the interface. So returns count is less than or equal to 0. Returns true. So I'll just put here. Returns true if count is less than or equal to 0. You can just do less than if you want. I do it equal to, you can just do equal to. I do less than just in case there's an error somewhere. So if it's negative numbers, then it'll still be empty. So public int size, return count. Whoops. Return count. So returns the size, which is just being tracked by the count. You can actually do this without a count. You just need to traverse more, I think. There is a way to do it with count, or without count. It just makes it a little bit more difficult. I think that's also a question too, like it could be a test question. How can I implement my data structure without a count? You may have to use a boolean or something for every iteration. So now we'll do toString. We'll override it too. So at override, what happened there? It always does that. At override, public string to string. So we're going to create an empty variable. Empty quotes. So string str points to empty quotes. Then linear node of type t. Temp points to head. We're going to traverse. So this is an object reference variable. It's pointing to head, so this location temp. So if head points to location like 001 in memory, then temp is going to point to 001. So we'll work with those. So while temp is not equal to null. So while temp is not equal to null. So we're not going to say get next, because we're not going to say, well, temp.getNext is not equal to null, because if the first element is null, then it's going to throw a null pointer exception. So if like the head is null, then it's going to throw a null pointer. Or and also if the I think if the head's get next is null, it will also throw a null pointer exception, and it won't work. So you just have to memorize it. So it's just for traversing a list, for a toString, you're gonna need while temp. If temp's pointing to head, so then you're gonna say while temp is not equal to null. Then we're gonna say str points str plus temp dot get element plus a space to separate it, or you can do a tab if you want. So then we'll say temp points at temp dot get next, then return str. We have to return str because it wants us to return a string. So here we're just setting an empty string variable to empty quotes, taking an object reference variable pointing it to the head node. Then we're saying while temp, so while head is not equal to null. While temp, which is pointing to head, so it's saying while head is not equal to null. str, which is this empty string, points to str, which is this empty string at this time, plus temp.getElement, so head.getElement. So if it's 5, then it'll be 5, plus a space, then temp points to itself, which is head.getNext, so head's get next. So if it's 6, then it's going to be pointing to 6. When it comes down to these brackets, come back up to the condition. Well, temp, which is now 6, is not equal to null. str points to str, so 5, because str is carrying the value 5. 5 equals to 5 plus, because of the space, we had a separation, plus temp.getElement, which is 6, plus another space. Then temp now points to temp.getNext, so 6 is the next one's 11. Then temp goes from 6 to 11. We come back down to these brackets, loop back up to the condition. Then while temp, which is now pointing to 11, is not equal to null. 5 and 6, which is str, 5 space 6 equals to 5 space 6 plus temp.getElement, which is 11 plus a space, so it keeps doing that over and over again. That's all it's doing. So that's it, except for the contains and 3 remove methods. We could also do an index of, but we'll do that in the doubly linked list, just because I think it's actually that we could try doing it maybe. So now we're going to start adding. So we're going to do the unordered list, then unordered list, and it's going to extend linked list. So we're going to create a class. Right click src folder. So we'll put a linked unordered list .java. So we'll just write it again. So public class linked unordered list of type generic type T extends linked list of generic type T, implements unordered list ADT of type T. So it's a little bit long one, a little bit of a longer one. So all it's saying is we have a linked unordered list. It extends a linked list, so it is a linked list, and it implements unordered list ADT. An unordered list ADT extends list ADT. So it's good practice extending interfaces and stuff. practice inheritance. And you can try making the list, we'll try making the list abstract, just for practice. You might get extra points on a test or exam if you maybe make it abstract, since we aren't instantiating it. But it might not work because we might not have any abstract methods, so we'll try it after. So we have our header, and we'll do our constructor. So public linked unordered list calls just the super reference, which is going to set up the super class's instance data, the fields. It's going to instantiate them with the parameters and the constructor and stuff. So now we'll have a public void add to rear. So you're going to add the data to the end of the list. So if you're storing data for your app or something, you want to put it in, you want to just tag it to the end, so that's all it's going to do. So we'll say linear node of type T, so we're going to actually, so when we add to rear, let's just say we're going to, let's say instantiate a new, we're going to instantiate a node. We should say a linear node. So for every time we add something, we're going to have to create a node to add. So here we're going to instantiate a linear node. So we're going to say linear node of type T. Node points to new linear node of type T. Takes an element as a parameter, because in our linear node class it has two constructors, and the one with the parameter is the one we're going to take. So we have here instantiate a linear node, done. We have instantiated a new linear node. This linear node is going to get its own memory location. We'll see that in the debugger. So here I have if head is equal to null and if tail is equal to null. That works. I think if you can also do if is empty, but we'll do it this way just because I've already written it this way. You can do if is empty too, it should work. I think I did switch some of them around. I did do if is empty. So if head is equal to null and tail is equal to null, then head points to node. So if it's saying there's no nodes in the list, if it's completely empty, it's blank, there's no data, it points to null. Then we'll say the node that we're adding here. Then we'll take our head reference, object reference, right here, linear node object reference of type T. It's from our linked list class. We're going to set that because this extends linked list, so it has those access to those variables. Linked or unordered list is a linked list, so we're going to take our head reference, object reference, and point it to that node. So we're going to say now head points to node. If we were using sentinels, we would actually have to, instead of head, we'd have to create two nodes, an actual instantiation, not just a object reference. We'd have to say linear node of type T, node points to new linear node. Then we'd have to pass in probably an empty, because again, it doesn't hold anything. Then every time that's all it is, and every time we traverse, we just skip the first one. That's all it is. It's just a sentinel. Sentinel is just their big, I can't remember, but from like MapleStory, that's the only time I've actually seen it. I think it's those big stone things. They're just like blocks, like those huge blocks, stone creatures, and they just stand. Like they block stuff, right? So that's all it does. It just stands in the order. So it's one at the front, It's like a guardian. It just stands at the front, and one at the end just it stands at the back. That's all it does. It's just a big. Just think of it like that. It's like a big statue that like could move or whatever. So head points to node and then tail points to node. We'll try to do that after. So head points to node, tail points to node, and if it's not empty, so we'll have else. So if head does not equal to null and tail does not equal to null. Notice how we didn't say or here, or it would change. Because then only one would have to be null, but because at all times head and tail will always have an element if there's a node in the list, because if there's one element in the list, then both are going to be pointing to the same node. If it's empty, both are going to be null. If there's two nodes, then they're going to be different. But at all times, they'll have an element to point to. So here we'll say else add to rear. So if head's already pointing to an element, then we're not going to take head and point it to the next one, right? We're going to set our tail and call set next to node. And then we'll reset our tail to point to the new node. So I'll explain it in a sec. So count plus plus, mod count plus plus. So what are we doing here? So we've explained this one. So if it's not empty, if there's at least one node in there, so let's just pretend there's one node. Head and tail both pointing to 5. So else, we've now instantiated a new node to add 6. It's holding 6, it's a node, it's holding 6. Then we'll set tail dot set its next reference. Tail, set your next, so tail's actually pointing at this point in time. Tail's pointing to 5, right? So we're saying tail. We'll go through this through the debugger if you're not understanding. Anyways, it's just if I do the examples here, it's going to take longer, so we'll do it after, don't worry. So we're saying tail, if it's pointing to 5, and head is also pointing to 5, then tail is pointing to 5 right now. So we'll say tail point your next reference to node, which is referencing this node, which is 6. So now tail points to 6. Then it's saying the tail's next points to 6, sorry. Tail's next reference points to 6. Tail's actually pointing to 5 itself, but its next reference is pointing to 6, so that can be a little confusing. Because if we say tail point to node, then its next then 5's next reference will never get set. That's what happens. And the way we link them in a linked list is with next and previous. In this case, it's a singly linked list, so we're linking it with next. So I hope you understand. We'll come back. So then tail again is reset to point to the new tail, which is 6, because we don't want it pointing to 5. Because if it's pointing to 5, then it's not pointing to tail. It's pointing to head, and the tail is not going to be correct. Then after that, that's it. We increment count by 1 and mod count by 1. So next one's add to front. I think it's even easier than that one. So we for add to front, we just have to switch the head reference. So we have public void add to front. Takes a T element. It's gonna have some more water, sorry. I think I'm not a pro YouTuber, but I think they actually like comment this stuff out. I mean, I don't even hear them sneeze or like cough or burp or anything. so you should hydrate too. Okay, so now we have a public void add to front t element. So it takes a t element as a parameter. And then what are we going to do? When we add to front, well, what are we going to add? Again, we have to instantiate a node. So here we'll comment just to remember, instantiate a node, a linear node. So here we'll say linear node of type T. Call it node again. You can call it whatever you want, but node's fine. You can call it front node, whatever. Node's easy because you don't want to get too mixed up. They're just local variables, so again, that's why we can call them. We can have more than one because each one's local. So this node's only going to represent to this method, and this node is only going to be relevant to this method as well. But these global variables like head from the linked list and tail, they change every time we set them. So linear node points to new linear node of generic type T, or I'm just going to say type T from now on. Try to. Then we'll pass in an element as a parameter. So let's say we're trying to add like 4 to the front, then we're going to pass in 4 for the element. What we probably won't, we'll try to, if we do that method, we'll probably just be adding 5. But you can add strings as well. This should work with strings. We'll get into that in a sec. So to do that, we're going to have to use dot equals to compare objects instead of equals or equals equals. That way it can compare strings. And it compares strings by the Unicode. It compares them lexicographically using the Unicode Latin alphabet, where each letter has a code associated with it, a numeric value, and symbols. So then we'll say if head points to null. You can say is if empty, I think, and tail points to null. Then we'll set head point to node again, and tail pointing to node as well. Then we'll say else node dot set next to head, and head points to node. Count plus plus and mod count plus plus. So all we're doing here is if we get this one, if it's null, we've already gone over that. Again, if it's null, we're just setting the head and the tail to the node. They're going to be pointing to the same node because there's only one element. So if it's not null, then we're going to say, so if it has at least one element, then we're going to take our node. Let's say it's 5, and let's say in the list there's 6, and 5 is what we're trying to add. So currently there's 6 in the list, and in this node it has the element 5. So we're saying node, which is this value here, which is 5. The node holding 5. We're going to set that node to point to head, which is currently 6. So it's saying, okay, 5, take your next and point to 6. And it's saying, okay, head, now reset to point to 5 from 6. So before this line was executed, so okay, so node.set next to head, 5 points to 6, you get that, this node, dot next, set it to current head, which is, current head is 5, sorry, current head is 6, so 5 dot set next, so 5, which is this node that we're just instantiated, set your next reference to point to the current head, which is 6. Now it's saying, okay, current head, now point to 5 because that's not the head now. 5's the head now. So that's it, we're just swapping it. Then count plus plus and mod count plus plus. So it's just the time complexity of this is I think it's O of 1. It's constant because it's just one shift. Big O's of, so the big O notation, time complexity, there's some other names for it. The order, it should be big O of 1, and this one should also be big O of 1 too, because we have a tail and if we have a head. If we didn't have a tail for this one would become big O of n, because it'd have to traverse, but we don't have to. If we're adding to the middle, we will have to traverse. So we'll do that one now. Whoops. Okay, so we'll do public void add after. So public void add after takes a t element and a t target parameters. So we'll go under here, public void add after t element takes a parameter t element and t target. So we're going to, I think I forgot, but we're adding the element after the target. I think that's correct. So we're gonna, again, we're going to, if we're adding something, we're gonna have to instantiate a node. Instantiate a linear node. This one should be O of n, I think. O of n time complexity. Big O. Because we have to traverse. I'll try to do a video on the algorithm analysis stuff. So instantiate a linear node. So we're going to say linear node of type T. Node points to new linear node of type T. Then pass in element as a parameter. Then we'll say if head equals to null, or you can say if is empty. We can try changing it after to see if it works. If is empty works. Did we do that before? No, we did not, because we're just adding. We don't need to check if it's empty. But we can just call is empty here. Try that. Then we'll say system.out. We can throw an exception as well. Actually, you know what? Let's just do this. If head is equal to null and tail is equal to null, then system.out dot print line empty list, and we'll just return. We can't return null because it's void. Maybe that's why we should it's optional, but we maybe should throw an exception here with is empty. We don't have to use is empty, we could just throw a new empty collection exception. So then here I don't think we need an else, because I wrote an else here, but that should be fine. So we'll have a linear node of type t, temp. I have a temp points to head here. You can just do that in one line. Do we do that above? Linear node in toString maybe. Linear node temp points to head. Linear node type t temp points to head. It should be, yeah, that's fine. Anyways, we save some space. So we'll say while not. So actually we're going to need another one. Another parentheses. Then we're going to put a not here. Actually, we're going to do it on the same, in the same parentheses. So while not, temp dot get element. So while temp dot get element does not equals target. So we're using equals here. If we just use the equals sign, it's going to just compare the numbers. It's not going to work when it might even throw an exception if we try to compare strings. So to do that, we can compare both, I think. And temp dot get next does not equal to null. So this condition's a little hard. It's kind of a longer one. So all it's saying, while temp, excuse me, while temp dot get element, which is, so temp is pointing to head. So while head dot get element does not equal to the target, and temp dot get next, so head dot get next, does not equal to null, then we'll set temp to point to temp dot get next. Temp points to temp dot get next. So it's and not or, so both conditions have to be true. So if one is not, then it's going to be false. So that both conditions have to be true for it to go to the next, to check the next element. Because what is this doing? It's checking our list to see if it's looking for the target. It's searching. So it's saying while temp dot get element, so while head dot get element, because temp's pointing to head in this case, does not equal to, let's say head points to 5 and we're looking for like 0, or no, we're looking for 1. So let's just say, just as an example, 5 and 6 are in the list, and we'll say target is 0, or target is 1. So let's say temp points to head. So while temp dot get element, which is 5, does not equal to 1. That's true. And temp.getNext, so 6 does not equal to null. Temp points to temp.getNext, so now temp's going to point to 6. So while, so now we've looped back up here, temp points to temp.getNext. Temp points to 6 now. Come back to the bottom brace, back up to the condition. So we loop from here, back up to here, to the condition. Then we'll say while temp does not, so while temp, which is 6, does not, so while temp.getElement, which is 6, does not equal to the target, which is 1, which is true, and temp.getNext does not equal to null. Well, it's now null, so it's going to skip. So now let's change it. Let's say this is 1, and so now the first element's 1, and we're looking for 1. So while temp, so now we've restarted again. So while temp.getElement, so temp, which is pointing to head, which is pointing to 1, does not equal to target. Well, that's false because it's saying while temp, which points to 1, does not equal to target. So while 1, that's all that's saying, or that part is saying. While 1 does not equal to 1. Well, does 1 not equal to 1? No, that's false. So if one of the conditions is false, then this whole thing will get skipped. So that means it's been found. So that's all that's doing. So here we check here. So if temp.getElement dot equals target. So if the temp.getElement does equal to the target, then node set your next to temp.getNext. Excuse me. So it's saying node.setYourNext to node set your next reference to point to temp, which is okay. So if we're going to add after, we're going to look for a target and we're going to add after that target. So node set your next to point to temp.getNext. So it's a little confusing here. So if we have like 5, 6, and 11, no, let's say we have 5 and 6. We found 5. Let's say our target was 5, we're trying to add 11. So node, which is holding 11, actually, let's say there's, maybe let's just say there's our target 6, and we're trying to add 11. So if we're saying, okay, if temp now points to 6, then if temp.getElement equals target, so 6 equals 6, that's true, then node, which is 11, set your next to point to node. So it's saying node set your next, which is 11, set your next reference to point to temp, which points to 6.getNext. Well, 6.getNext only points to null. So if it's the last element. If we're adding in between, that's going to change. So if we're trying to add, let's say our target's 5, so 5 and 11 are in the list. So we're adding, so T element is 5 and T target is, T element is 6 and T target is 5. So we're adding 6. So T element is 6 and T target is 5. So we're adding 6 after 5. So if we found 5, if temp.getElement, which is 5, equals target, which is 5, then node, which is 6, set your next to temp.getNext. So it's saying, so if there's 5 and 11 in the list already, so it's saying, we're going to go through this in the debugger, but we're saying node, which is, what do we say what it was? 6, set your next reference to point to temp, which is head, which points to 5, .get next, which at that time it's 11. So it's saying 6, set your next reference to 11. It might be a little hard to picture. That's why the debugger will help. But that's it. Those are the only conditions, I think. I did code this myself, so if there's I think I checked all possibilities, but you can, if there is something, you can just fix it. It should work. I did test it. So then we'll say temp.set next to node. So then it's saying temp set your next. So if temp is 5, then 5 set your next to 6. That's all it's saying. And 6 is next is set to 11. Here we're going to compare memory location. So we're going to say if tail.getNext points to node. So here we're going to compare memory locations with equals. So if the current tail next reference now points to the new node, so basically we have a new tail, then we're going to set the tail. So tail gets set to node. So if tail.getNext is equal to the node that we just created, then tail now points to node. So we're just comparing the tails. So if tail, which is currently 6, .getNext, which is 11, is equal to node, which is also 11. Let's pretend. Then tail, now we're going to set tail to point from 6, it's going to point to 11. So it was previously pointing to 6. Then we're going to point it to 11 now. That's it. Resetting the tail. Count plus plus, and then mod count plus plus. So if all that's false, then we'll say system.out.println target is going to get the variable. Then we're just going to say not located or not found. So if we're looking for something and we didn't find it in the list, then it's going to return. Once it iterates through all the elements, if it realizes it didn't find it, then it's just going to say not located, and it's going to, our method will be over. We can actually do a return. We don't need to. So that should be it. We still have to do the removes. So it's been an hour now. We still have to do the removes. Let me just check my notes here. I think it's just the removes and the contains. So it should be 3 methods. 2 of them are pretty easy. Remove first, remove last. Then remove. Then contains is easy too. And then the add method. Oh, we also have the add the unordered list. Oh, sorry, the ordered list. Excuse me. That might take a while, actually, another hour. Then maybe another hour to test. So I'll take a break and I'll come back.